Hi everyone and welcome back. In this video, I want to provide an introduction to recursion. And more specifically, we're going to write our first recursive function. So you may have heard of the term recursion or the term recursive before, perhaps from your everyday vocabulary or perhaps from your math background. So I just typed into Google define recursion and I wanted to show you the definition. So recursion is a noun that means the repeated application of a recursive procedure or definition. Okay, so the definition of recursion itself uses a different form of the word. It uses the word recursive. So let's take a look at what recursive means. All right, recursive is an adjective that means characterized by recurrence or repetition. And I think this repetition part here is real important because we're going to see that every recursive solution we write can actually be implemented using iteration, meaning loops. So the idea of repetition that you know from loops can really be applied to recursion. All right, you can see there's a mathematics/linguistics subdefinition here, and there's a computing subdefinition as well. This subdefinition here for computing, I think, is a little convoluted. So I'm going to head over to this kind of subpanel over here where there's a little preview of the Wikipedia page for recursion. And I think this one is a little more approachable for beginners. Recursion occurs when a thing is defined in terms of itself or of its type. Recursion is used in a variety of disciplines ranging from linguistics to logic. The most common application of recursion is in mathematics and computer science, where a function being defined is applied within its own definition. All right, I really like this introduction. This is great. So I'm going to head over to our notepad here and provide my short little definition for a recursion in computer science, and then my short little definition of a recursive function. All right, so for recursion, I'm going to write something being defined in terms of itself. So the most common example that we see would be a recursive function, which we're going to talk about here very soon. And another classic example I like to put in here would be a self-referential structure. So we worked with linked lists a few videos ago, and we defined a node struct. And that node struct, in its definition, had a member of type node pointer that pointed to the next node in the linked list. And at that time, I labeled it as a self-referential structure, right? We defined a node in terms of itself. A node definition had a member that was a node pointer, right? So remember, when we write our code, right, we finish, then we compile. So the definition is complete when we go to compile and run our code. So a node was defined in terms of itself, even though it felt kind of weird writing the definition for a node and then using that definition as we were writing it. But remember, we finished writing the definition before we compile, and then at runtime, then we're going to be able to make node objects. So same with recursive functions. It's going to feel a little weird writing a function that calls the function that you're still writing. But once you get done writing it, that's when you compile and run it, and its definition is complete. So what is a recursive function? So this is a function that directly or indirectly calls itself. So directly would be within the function body, there's a call to this function you're defining. Indirectly would be maybe it calls another function, and then that function calls the original recursive function. We'll see examples of this. All right, so to start off, I have a very straightforward example that I want to solve first iteratively, meaning with a loop, and then recursively, meaning with a recursive function. So the example is, let's write a function that accepts an integer argument n and displays a countdown. For example, if n equals 3, the function displays 3, 2, 1, blast off. So when the countdown gets to 0, instead of displaying 0, we're going to say blast off. So I'm sure you could solve this iteratively using a loop, right? A for loop or a while loop. And that's great. We're going to do that. And then we're going to say, let's solve it again without using a loop. Let's solve it recursively. And so you already might be wondering, well, if I can solve it iteratively, why do I need to solve it again recursively? Well, the answer is you don't, other than at this point to learn recursion. So why would you learn recursion? Two main reasons. So the first is Some problems have very short, very simple, very elegant recursive solutions. Those same problems have ugly, long, convoluted, iterative solutions. So there are just some problems out there that just lend themselves really well to recursion. Secondly, you want to be able to read other people's code, right? A lot of your career in software engineering is going to be working with teams and working with code that you didn't write. So if someone out there is using recursion and you see it and don't know how to interpret it or contribute to it, and then you're going to be in trouble, right? Recursion is super common, and it is programmer's choice whether they use it or not, but a lot of programmers do use it. So you need to be familiar with it so that you can work with those programmers, and so you yourself can write beautiful recursive solutions. All right, let's head over to the virtual machine and first code up this countdown solution iteratively. Then we'll code it up recursively. I've got a little 3-file format here set up where I've got main.cpp with an empty main. I've got recursion.h with just some boilerplate code here, and then recursion.cpp where we're going to write the definitions for our recursive functions. All right, so let's start in main. So I'm going to define a function in in recursion.cpp called iterative countdown. I'll call it in main. Let's call it with 3, so we see that 3, 2, 1 blast off. So its argument is going to be of type int, and it's going to be a void function. It's not going to return anything. In future videos, I am going to go through some examples of functions that return values. They're not that much trickier, but they are just a little bit different because you've got to keep track of what's being returned up the call stack. All right, now let's head over to recursion.cpp and let's provide implementation of this iterative solution. All right, so I'm going to simply have a for loop here that's going to start I at n, right? Because if n is 3, then I want to display 3, and then 2, and then 1. So I'm going to stop when I reaches 0, because I don't want to print out 0. I instead want to break out of this loop and then print blast off. And I'm going to be subtracting 1 each iteration. So I'm just going to put a space after each one of my numbers here. And then outside of this loop, I know that I is 0, so I'm going to see out blast off. All right, so let's try this out. All right, 3, 2, 1, blast off, looks good. Let's test it again with a higher number just to make sure that everything is working. All right, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, blast off, looks good. All right, we've solved this problem. Now let's solve it again using recursion. So I'm going to call this solution recursive countdown. We'll pass in 3 again, and then of course we'll come back and test it with 10. Recursive countdown. So it's going to have the exact same signature, except for the name. It's going to have an integer for n, and it's still going to be a void function. All right, so recursive countdown. In here, I'm going to take some notes to really introduce the different parts of recursion that can help you when starting to define your own recursive solutions. All right, so let's start with the elements of recursion. So number 1, we have a base case. So what is a base case? So this is when you stop recursing. So no more recursion is appropriate. Okay, so what would be the example of a base case for our countdown? Well, no more recursion or no more repetition is appropriate. So that would be when n is equal to 0. So that's when we want to stop recursing. All right, so let's write out the base case for our recursive countdown. So if n is equal to 0, then what do I want to do? Well, when I was equal to 0 in our iterative solution, we printed out blast off. We still want to do that. And then we want to return, okay? No more recursing. So that means we can pop this call off of the call stack and start popping the rest of the calls off the call stack until we can get back to main. Okay, so the key here with our base case is we stop recursing. No more recursive calls. All right, if we get here, then we're in the second element of recursion, which is the code to approach the base case. Okay, so this is going to be a reformation of a similar yet smaller version of the problem. So I'm going to put here like progress towards the Boolean condition being false for loops. You probably hear me say that a lot. So when I first introduce loops or whenever I'm working with loops, you always have to remember that eventually you want to stop looping, right? So you have this progress towards your Boolean condition being false, right? So that's what the I minus minus is here, right? Eventually we want this Boolean condition to be false so that we stop looping. Because an algorithm that runs forever isn't an algorithm, right? It has to halt, it has to produce a result. All right, so that's what our code to approach the base case is doing. It's that progress towards this if statement eventually evaluating to true so that we stop recursing. All right, so for us, what we want to do, we want to print out n and call this function again with n minus 1. So why n minus 1? Smaller version of the problem that is approaching 0, right? Remember 0, that's our base case right here on line 17. So I'm going to see out n and that space at the end, and then I'm going to have my recursive call or recursive step. So I'm going to call this function again, recursive countdown, and I'm going to pass in n minus 1 so that the next call to recursive countdown, n, the parameter, is one step closer to our base case of 0. And that's it. That is our recursive countdown definition. Very cool, right? Do you see the recursion part, right? So we are defining recursive countdown in terms of itself, right? We have this recursive call here where we're going to call this function again. And we're going to pass in a slightly smaller value of n so that as we keep repeating and calling recursive countdown, eventually our base case is true, n is 0, we print blast off and we return. When this function returns, right, to one of its recursive calls, there's no other line of code after line 26, so there's nothing to do, and we will return each one of these calls until we get all the way back to the original call on line 7 in main. All right, so let's try it. All right, 3, 2, 1, blast off. Let's try it with 10, just like we did with our iterative solution. And it looks like it's working. All right, it might kind of feel like magic right now that it's working, but let me show you something that you can do to kind of get more transparency into your recursive functions. So I'm going to put another cout statement in here. It's not required for the solution, and just saying something like returning from the, I'm going to say n minus 1 call. That's it. That way we can see the order at which our code is executing. All right, so let's look at the 3, 2, 1 blast off right here. All right, so we see the output from line 24 and the output from line 18 before we see any of the output from line 27. that still makes sense, right? These lines of code occur before line 27. Okay, so we see 3, 2, 1 blast off. And then in the reverse order in which recursive countdown was called recursively, we see those calls being popped off of the call stack. And the call stack really is like a stack data structure that you know of. So a stack data structure is a LIFO data structure, right? Last in, first out. So with last in, first out, we see that 0 was last in, right? That's what gives us a blast off. So it's going to be the first out, the first one popped off the call stack, then 1, and then 2. And then, of course, eventually 3, which is our initial call right here. All right, I want to draw a diagram now in order to kind of make this a little bit more transparent about what's going on. And then we'll call that an introduction to recursion. All right, so what I'm about to draw here is called a call stack diagram, where you can see each call of a recursive function and what the values are of that call. And then once you see the base case, you'll be able to see the call stacks being popped off, or the calls being popped off of the call stack. And they really are being popped off like you know of from a stack abstract data type and a stack data structure. Okay, so let's start with main.cpp. Okay, so main.cpp is going to call, I'm just going to write countdown to keep it short, countdown 3. Okay, so this call is being pushed onto the call stack, and that's where all of the local variables for this call to countdown will live. That's why we say that they're on the stack. They're statically allocated, they're on the stack. All right, so we'll say n is 3, and we'll just keep track of the call number. So this is call number 1. All right, next, we check to see if we've reached the base case at n equals 0. We have not, n is 3. So we're going to do our recursive call, our recursive step, which means we are going to pass n minus 1, which is 2, into another call of this function. So now these calls here are originating from recursion.cpp. Okay, these are our recursive calls starting with n equals 2. All right, so this is going to be the call for countdown of 2. So n is 2, call number is 2. We check how we reached our base case. Is n equal to 2? It is not. So we're going to have a recursive call passing in 2 minus 1 is 1. Okay, so this is countdown passing in the value of 1. N is 1. This is our third call to countdown. We check how we reach our base case. Is n equal to 0? It is not, so we're going to have another recursive call with n equal to 0. So now we have countdown of 0. This call, n is 0. This is call number 4. Okay, so it's our third recursive call, our fourth total call to the function from main, starting from main. Okay, we test our base case. Is n equal to 0? Yes, it is. N is equal to 0. Okay, so that means that we are going to return. So we're going to pop countdown sub 0 off of the call stack. There's nothing to do at the end of the body. I'll show you one more time here. Okay, there's nothing to do at the end of this body. So this most recent call on the call stack, countdown of 1, is going to return as well. So we're going to pop it off. Okay, now we're up here with the call when n is 2, and we're going to pop this off of the call stack. All right, then we're up here with our originating call. This wasn't a recursive call. There's nothing to do at the end of that function. So we are going to pop the originating call, the non-recursive one, countdown of 3, off of the call stack. And now control flow, execution flow returns to main. Okay, we go back to main because that's where we called countdown of 3 originally. All right, so let's go through this one more time, and this time I'm gonna, in red, write what is being printed out so you can see the order. All right, so let's assume we're in main. Main calls countdown, passing in 3, okay? We check our base case, we have not reached it, so then we're going to see out three. Okay, then we call countdown passing in 2. We have not reached our base case. Then we're going to see out 2. We call countdown again, passing in 1. We have not reached our base case, so we're going to see out 1. We call countdown again, passing in 0. We have reached our base case, so that if statement is going to execute, and we are going to see out blast off. Okay, and then we pop off the call stack, countdown 0, countdown 1, countdown 2, countdown 3, and that's how we get our 3, 2, 1 blast off. Now, at the end of this function, I did add this kind of returning statement. So I could add that in here as well, maybe in green, right? After we print out blast off, then we're going to see out returning 0. Then we're going to move up to this call on the call stack. We'll see out returning 1. Then we're going to move up to this call on the call stack. All right, not able to get rid of these artifacts here. That's okay. All right, now we're going to see out return. Ooh, now it's acting really, really crazy. Oh well, we're almost done. Hang in there. We're going to see out returning 2. We pop off the call stack, and then we're going to see out here returning 3. All right, that's it. That's our introduction to recursion. We did this with a void function, so we weren't returning any values. In the next video, I'm going to show you some examples where we're going to be returning values. Until then, just to recap, when would you use recursion? Okay, you would use it when the solution is much more simple or elegant or short and straightforward than an iterative solution, and there are a lot of problems out there that lend themselves really cleanly and really well to recursion. You'd also use it if someone else is using it and you're working with them on a team. Okay, the kinds of problems that can be solved using recursion have these attributes. They have one or more simple cases that have a straightforward, non-recursive solution. Okay, the other cases may be defined in terms of the problems that are closer to the simple cases. So that's like our recursive step here where we were subtracting 1 on line 26. And through a series of calls to the recursive function, the problem eventually is stated in terms of the simple cases. So this is kind of what's known as a divide and conquer approach, where you divide the problem into subsequently smaller problems in order to try and conquer the problem as a whole. A fresh copy of the function goes to work on a similar but simpler problem than the original. There can be a lot more memory overhead with recursive solutions compared to iterative solutions. Even in that call stack diagram I just drew for you, you could see that there is really a fresh copy of the function and all of its local variables being created and pushed onto the call stack. So there's a lot more memory overhead with recursive solutions than iterative solutions. So that's something to keep in mind. All right, that's it. Thank you for watching.